In the depths of the constellation of Sagittarius, there is an object around which the cosmos seems to be losing stability. Amid streams of red-hot gas and dazzling ultraviolet radiation, one of the most unusual stars in the Milky Way galaxy, WR-104, rotates. Its light is not like the ordinary glow of stars. It is a dying giant, shedding its own outer layers at a monstrous rate. The space around it is filled with vortices of hot plasma, carbon streams, and shock waves that can change the structure of the surrounding space for many light years. WR-104 belongs to the class of Wolf-Rayet stars, some of the hottest and most unstable objects in the entire Milky Way galaxy. Such stars have already exhausted most of their fusion fuel and are in the final stages of existence. Their cores are compressed under monstrous pressure, and their outer shells are torn apart by streams of stellar wind. The speed of these flows reaches thousands of kilometers per second. The gas is ejected so violently that a gigantic structure of dust and hot matter forms around the star.
But it is the WR-104 that stands out from the rest. Around it, there is one of the strangest shapes in the entire observable universe, a spiral of glowing cosmic dust. This structure stretches for billions of kilometers and resembles a giant rotating vortex swirled by the forces of gravity and radiation. The spiral continuously expands in a vacuum, maintaining an almost perfect shape. Inside it, particles of carbon, oxygen, and heavy elements ejected from a dying star move. The reason for the appearance of this structure is hidden in the WR-104 system itself. It is not a single star. A massive blue companion rotates next to her. The two objects are so close to each other that their stellar rings collide with colossal energy. At the point of collision, the temperature rises to millions of degrees. Streams of matter are compressed by shock waves and create conditions for the formation of cosmic dust, even in such an extreme environment. It is these collisions that give rise to a giant rotating spiral that goes into the darkness of interstellar space.
Each revolution of the system seems to carve out a new turn in space. The radiation of WR-104 is so powerful that it is capable of ionizing huge regions of gas around it. Turbulent plasma fronts are constantly appearing inside the surrounding space. Electromagnetic fields are stretched and bent. Particles are accelerated to enormous speeds. The cosmos around the star resembles a region of continuous destruction of matter. The main reason why WR-104 is getting so much attention has to do with its future. Such stars do not end their existence peacefully. Their finale is associated with one of the most destructive catastrophes in the universe, a hypernova. This is an explosion whose power exceeds ordinary supernovae many times over. At the moment of core collapse, the star can eject a colossal stream of gamma radiation, X-rays, and relativistic particles.
It is the gamma-ray burst that makes WR-104 especially dangerous. During some hypernovae, narrow energy beams are formed, escaping from the poles of a dying star at almost the speed of light. If such a beam is directed towards a planetary system, the consequences can be catastrophic. The stream of gamma radiation is capable of destroying the atmospheric layers of planets, causing powerful chemical reactions and changing the balance of radiation in outer space. For many years, there has been a hypothesis that one of the poles of WR-104 could be oriented towards the solar system. It was this idea that turned the star into one of the most discussed objects in modern astrophysics. Even the possibility of such a coincidence has given rise to a huge amount of research. Later observations showed that the orientation angle of the system probably differed from the initial estimates,
But the threat itself did not completely disappear. The structure of the star remains complex, and the exact geometry of the emissions is not fully defined.
WR104 is about 8,000 light-years from Earth. By cosmic standards, this is a relatively short distance for an object of such power. The light from it has been passing through the interstellar medium for thousands of years, crossing clouds of gas and dust, passing through the spiral arms of the galaxy, and reaching the inner regions of the Milky Way. The surface temperature of WR104 exceeds tens of thousands of degrees. The core of the star is even hotter. Inside, heavy element synthesis reactions continue. Helium is converted into carbon, oxygen, and heavier nuclei. The pressure inside reaches colossal values. Gravity tends to compress the star, and thermonuclear processes try to keep it from collapsing. But the equilibrium is gradually being destroyed.
Wolf-Rayet stars lose mass incredibly quickly. WR104 ejects huge volumes of matter into the surrounding space every year. During relatively short space periods, it can lose a significant part of its mass. These emissions gradually enrich the galaxy with heavy elements. It is these objects that create carbon, oxygen, and other elements that later become part of new star systems, gas clouds, and planets. A dense shell of cosmic dust is observed around WR104. It absorbs part of the radiation and glows in the infrared range. Telescopes capture the complex structure of the spiral, which is constantly expanding. Each new orbit is a trace of the next orbital movement of the system. The spiral moves outward at the speed of the stellar wind, gradually dissolving into the interstellar medium.
Even against the background of other massive stars, WR104 looks extremely unstable. Its internal processes are already approaching the final phase. When the nucleus loses its ability to sustain thermonuclear reactions, the pressure will no longer compensate for gravity. An instantaneous compression of the internal regions will begin. The temperature will rise sharply. The substance will rush to the center. This will be followed by a gigantic burst of energy. A hypernova explosion is capable of surpassing the brightness of the entire Andromeda galaxy for a short time. The shockwave will rush through the surrounding space, breaking up the gas clouds and accelerating the particles to relativistic speeds. Magnetic fields will be distorted by colossal flows of energy. The outer shells of the star will scatter for millions of kilometers. The remnant of the core can turn into either a neutron star or a black hole.
If a gamma-ray burst is formed during the collapse, the energy will be concentrated in a narrow beam. Such rays are considered to be one of the most powerful phenomena in the universe. In a few seconds, they were able to release more energy than ordinary stars emit in billions of years. The radiation pierces the interstellar medium and can propagate over vast distances with almost no attenuation. Gamma-ray bursts remain one of the greatest mysteries of modern astrophysics. Some of them are recorded in distant triangulum galaxies and are visible billions of light-years away. Their brightness is so great that detectors detect signals even after passing through vast regions of space. If a similar process occurs at WR104, the outburst will be one of the brightest events ever observed in this part of the galaxy. The star itself already resembles an object on the verge of complete destruction. Its outer layers are constantly torn apart by the stellar wind. The density of matter changes due to instabilities in gas flows. Powerful shock fronts arise inside the system. The orbital motion of the stars twists the ejected matter into a perfect cosmic spiral. WR104 is sometimes called one of the most beautiful star systems in the Milky Way. But behind this beauty, there is a monstrous energy. A luminous spiral is not a calm formation,
but a trace of the destruction of a star that gradually loses its own structure. Each new portion of the ejected substance brings the system closer to its final collapse. In the central regions of the star, the pressure continues to rise. Heavier elements begin to form more and more quickly. Such reactions occur less and less. If hydrogen fusion can continue for millions of years, then the final stages of the evolution of massive stars proceed much faster. Some processes last only thousands or even hundreds of years, an instant by cosmic standards.
WR-104 remains one of the main laboratories for studying the last stages of the existence of supermassive stars. Observations make it possible to study the structure of stellar winds, the processes of cosmic dust formation, and the mechanism of formation of gamma-ray bursts. Infrared telescopes record the expansion of the spiral. Spectral analysis shows the composition of the ejected substance. Radio observations help track the movement of shock waves within the system. Even the surrounding space around WR-104 gradually changes under the influence of its radiation. Gas clouds heat up and ionize. The interstellar medium is saturated with heavy elements. Particle streams create turbulent structures in magnetic fields. The cosmos around the star becomes a region of continuous energy instability. Someday, this system will disappear. A spiral stretched in a vacuum will be torn apart by a hypernova shockwave. Huge masses of matter will rush into interstellar space. In place of the star, a compact object with colossal gravity will remain. But even after the death of WR-104, its matter will continue to move through the galaxy. Atoms of carbon, oxygen, and heavy elements will mix with giant molecular clouds, from which new stars and new cosmic structures will later emerge. In the meantime, WR-104 continues to rotate inside its own death spiral. Plasma streams collide with monstrous force. Cosmic dust swirls into giant coils. Ultraviolet radiation burns through the surrounding space. Inside the core, the struggle between pressure and gravity continues. And somewhere in the depths of this star, a finale is already forming, capable of turning one object into a source of energy, which for a brief moment will become brighter than billions of stars in an entire galaxy.
After the collapse of such stars, space never returns to its previous state. The hypernova shockwave tears the environment into giant fragments, creating expanding shells of hot gas. The temperature inside such structures reaches millions of degrees. X-rays penetrate the remnants of the explosion, and magnetic fields begin to bend chaotically under the influence of monstrous energy. If WR-104 enters this phase, its spiral will disappear in a matter of moments, dissolving into the flow of plasma and radiation. Even now, the system already resembles an object balancing on the edge of stability. Heavy elements accumulate inside the nucleus. Each new stage of thermonuclear fusion occurs faster than the previous one. After carbon, the formation of more massive nuclei begins. The temperature rises so much that the matter inside the star gradually loses its usual properties. Electrons break out of atoms. Matter turns into a super-dense plasma, compressed by monstrous gravity.
In the central regions of WR-104, there may be streams of matter moving at tremendous speeds around the nucleus. These processes create instabilities that can change the structure of a future explosion. Some models show that such stars can experience powerful mass ejections before they die. During such periods, the outer shells are literally torn apart by internal pressure, throwing gigantic volumes of gas into space. Sometimes, such emissions become so powerful that additional shells of matter form around the star.
The density of WR-104's stellar wind is so high that the system appears shrouded in a glowing haze. Streams of carbon dust absorb some of the light and re-emit it in the infrared. It is thanks to this that the spiral is especially clearly visible to infrared telescopes. In the pictures, it looks almost unreal, a perfectly symmetrical vortex swirling in the silent darkness of space.
Each revolution of this structure corresponds to the movement of two stars around a common center of mass. As the system continues to rotate, the spiral grows. New layers of dust are pushed out. Older orbits recede into interstellar space, gradually dissolving among the rare gas of the galaxy. But inside the near regions of the spiral, a high density of matter is preserved. There, shock waves continue to collide and heat matter to extreme temperatures. WR-104 itself belongs to the Wolf-Rayet carbon stars. This means that the outer layers are already saturated with carbon, formed in the interior of the star. Such a state indicates a late stage of evolution. Hydrogen has practically disappeared from the outer regions. A significant part of the shell has already been lost. The inner core becomes increasingly unstable.
Some astrophysical models suggest that such stars can rotate at tremendous speeds before collapsing. If the core of WR-104 does maintain a rapid rotation, this increases the likelihood of a directional gamma-ray burst. During collapse, matter around the core can form an accretion disk, and some of the energy will be ejected in the form of narrow relativistic jets. These streams break through the outer shells of the star and burst out into space at almost the speed of light. Such jets are able to maintain structure over huge distances. They carry colossal energy in a narrow direction, turning the star into the source of one of the most powerful types of radiation in the universe. At the moment of the outburst, gamma radiation becomes so intense that it can exceed the brightness of all other objects in the galaxy combined.
Turbulent vortices are constantly occurring in the outer layers of WR-104. Plasma flows collide and fragment into shock fronts. These processes create instabilities in the structure of the stellar wind. Sometimes the density of the substance changes so dramatically that bright knots and seals appear inside the spiral. They move outward along with the general flow of matter, gradually cooling in interstellar space. Even the surrounding region of the Milky Way is affected by this system. Radiation from WR-104 penetrates through clouds of gas, ionizing hydrogen atoms. Particle fluxes change the structure of local magnetic fields. Inside the interstellar medium, shock waves arise that propagate over vast distances. The cosmos near the star has long ceased to be calm. Among the massive stars of the galaxy, WR-104 is considered one of the most unusual precisely because of its geometry. Most Wolf-Rayet stars are surrounded by chaotic clouds of matter, but a near-perfect spiral has emerged. Its shape is so precise that it resembles a giant cosmic mechanism that continuously spews coils of hot dust into the void.
Inside the nucleus, meanwhile, the synthesis of heavier and heavier elements continues. When the elements of the iron group begin to form, the star approaches the critical boundary. Iron does not provide energy during thermonuclear fusion. At this point, the internal source of pressure begins to disappear. Gravity takes precedence. The core shrinks rapidly. In seconds, processes take place that can change an entire star system. Collapse can give rise to a black hole. If the mass of the core is too large, no pressure can stop the compression. Space and time will begin to bend so much that a region will form from which even light cannot escape. Around the newborn black hole, there will be expanding hypernova remnants, red-hot clouds of heavy elements and plasma.
Such events are considered to be one of the main sources of heavy elements in the universe. During the explosion, gold, uranium, and other massive nuclei are formed. Shockwaves carry them through the galaxy, mixing them with interstellar gas. Later, these elements become part of new star systems. The matter of the dead giants continues to travel through space for millions of years.
WR-104 is already radiating energy in huge volumes. Its luminosity is many times higher than that of ordinary stars. Most of the energy is spent in ultraviolet radiation and powerful stellar wind. Streams of matter continuously carry away the mass of the system into the surrounding space. This makes the star less and less stable. There are suggestions that the last years of the existence of such objects may be accompanied by sharp changes in brightness. Internal instabilities can cause flares and increased mass ejections. Sometimes, such processes create dense shells of gas around the star. When a hypernova shockwave later collides with these shells, additional energy is released. As a result, the flash becomes even more powerful. Against the backdrop of the endless darkness of the galaxy, WR-104 looks like a slowly rotating energy vortex. The spiral continues to grow. The gas is heated by shockwaves. Dust scatters infrared glow. Instability gradually accumulates inside the core, which will one day destroy the entire system.
And as the light from WR-104 continues to cross thousands of light years of space, the star itself is already approaching the point where its existence will turn into a giant flare, capable of briefly eclipsing entire regions of the Milky Way, leaving behind only an expanding cloud of red-hot matter, and an object with gravity capable of bending the very fabric of space. And as WR-104's shell continues to thin, the inner workings become more exposed, as if the star itself is losing its last layers of protection, revealing its red-hot heart to the cosmos. Streams of matter no longer just burst out. They form stable channels of mass leakage, through which energy escapes in continuous jets. In these jets, structures are born that resemble waves, twisted and torn at the same time, as if space does not have time to react to the speed of what is happening. In the depths of the system, a slow but irreversible redistribution of matter continues. The outer layers, which have lost stability, are no longer held back by gravity in their previous form. They fragment to form dense clumps that move through the rarefied medium of the spiral, colliding and collapsing. Each such clump carries traces of the star's internal reactions, imprints of the conditions under which heavy elements formed, from carbon to more massive nuclei that appeared in the last stages of life.
The radiation is becoming more and more harsh. Ultraviolet light is gradually replaced by the X-ray range in certain areas, where temperature and density reach local maximums. The cosmos around the star ceases to be homogeneous. It turns into a layered structure of energy, where each zone lives according to its own physical laws, depending on the distance to the source and the density of the ejected matter. The spiral shape, which has become the symbol of WR-104, gradually loses its perfect symmetry on large scales. The outer coils stretch, bend, and interact with the interstellar medium. The galaxy's gas resists the movement of the ejecta, creating slowdowns and local seals. These areas begin to glow faintly, but more densely, as if leaving traces of a collision between the stellar wind and the cosmic void. Within the system, the rotation of two components continues, and it is this rotation that remains the main mechanism that holds the structure of the spiral. The orbital motion does not weaken, but the gravitational interaction gradually changes the distribution of mass. Any loss of matter affects the balance of power, and the system slowly rebuilds its own dynamics, as if adjusting to a new reality in which stability becomes a temporary state.
The core of WR-104
begins to be dominated by processes characteristic of the final stage of the evolution of massive stars. Thermonuclear reactions no longer create a stable energy balance. They flare up in layers, in separate shells, where conditions still allow the synthesis of heavier elements. These reactions are uneven. They occur in leaps and bounds, creating an internal pulsation of pressure. Each such pulse propagates through the star, causing microscopic but significant changes in structure. These oscillations gradually prepare the conditions for the final destruction. At some point, the internal pressure will no longer be able to compensate for the mass of the core.
Then rapid compression will begin, in which the substance will lose its usual shapes.
The electron shells of atoms will be destroyed, and the nuclei will be so close that they will begin to interact under conditions inaccessible to ordinary matter.
From the outside, this process may not manifest itself instantly. The luminosity of the star will remain for some time, supported by residual reactions and the energy of the falling matter. But the structure will become different, hidden from observation in the visible range, denser and more unstable than before. Meanwhile, the spiral around WR104 continues to expand into space. Old coils go far from the source, cool and dissolve, losing their brightness. New ones form closer to the system, where there is still enough energy to ionize and heat. This continuous process gives the impression of an infinite mechanism, although in reality, each new structure is only a temporary trace of ongoing decay.
Destruction is already embedded within this mechanism. It does not occur instantaneously, but accumulates in the form of changes in density, pressure, and composition of matter. When the critical point is reached, the entire system will be rebuilt in a very short time. Gravity will prevail, and the final fall of matter towards the center will begin. This moment will be the beginning of a colossal release of energy. The shock wave will pass through the layers of the star, tearing them apart from the inside. The outer shells will be ejected into space at tremendous speed, forming an expanding cloud that will eventually become part of the interstellar medium. The inner core will either shrink to the state of a neutron star or disappear beyond the event horizon, turning into a black hole. And even after that, the space around will not become empty. It will remain filled with traces of what happened. Particle flows, magnetic anomalies, clouds of enriched matter. These traces will slowly dissipate, but will not disappear completely. They will become part of the galactic environment from which new star systems will one day begin to form again.
WR104 already exists in a state where the past, present, and future of its matter are intertwined. The spiral shows traces of past ejection. The core forms future destruction, and the surrounding space fixes the current state of equilibrium, which is no longer stable. And as the light of this system continues to move through space, the star itself is getting closer to the point where its structure will cease to exist as a whole, dissolving into one of the most powerful events available to the universe.